Okay, hello. In this video, we're going to talk about surface area and volume a little bit. And I just happen to really enjoy math. And so I wanted to make a math video where we're going to work through a couple problems, or more like a two-part problem involving a particular shape. Before we do that, here's just kind of a fun thing. This is a little Unity program that I'm working on. I don't know if it'll ever be impressive, but currently it works, and that's what's exciting to me. Is it just I wanted to graph three-dimensional parametric equations, so I didn't find a good grapher online that really did what I wanted it to do easily. So I just kind of made my own, and the code on the left-hand side is the code. It's like really short. It's it would need a lot of work to be user friendly, but for me, I can use it, with editing in the code just fine. And you can see I graphed a little parabola there, which happens to be 2D, but the axes are 3D, and it's no harder to go from 2D to 3D in that particular environment. So there's that little fun thing. Oops, where did I? Okay, so back to our surface area and volume. So what we're going to be working with is a right cone. And if you looked at a right, I don't know how well I can draw a circle. Let's try. So if you looked at a right cone staring at the base, you would see what is a perfect circle. And that's my freehand attempt to make a perfect circle. And it'll have a center and a radius going out to the outside, right? If we were to tip that up and look at it, say like you're holding an ice cream cone, then roughly it would look like that. This is the cone that we're going to be working with. And once again, it still has from the center, the outside, that's the radius. From the center of the base, I'm calling it, even though it's upside down right now, normally they would be viewed like that. So that's why this is called the base. But anyway, so still this circle edge is the base. If we go from the center of the base down, in this case, to the top, that is what we call H, and for height. And if we run along the outside edge, then we have what we'll call L, and it's for slant height. And in this particular example that we want to work through, R is going to be 3, H is going to be 4, and L is going to be 5. I think the reason for that will become apparent in a minute. So let's take our cone and let's actually lay it on a coordinate plane. And we want the center to go through the x-axis. Let's see if I can try to sketch this out well. Okay, imagine, you just have to use your imagination a little. Trust me, it's a perfect right cone, and the center of the x-axis goes through the center of the cone. So we have our base here at the end. And now you might notice that you could nicely fit a perfect right triangle into this cone. And if you were going to take this this right triangle that I just sketched, so like here's the angle theta. That would be an angle in the right triangle. And I drew the little box to show that it's a right triangle. That particular triangle right there. Maybe I can even do some little lines. Yeah, those are showing up. So this right triangle, okay, if we take that right triangle and we rotate it 360 degrees around the x-axis, so taking it and rotating it around the x-axis like that, we would make our cone. That the shape that would be traced out by that rotation would be our cone shape. So we're going to play with that idea. And as I laid this on the side here, the height of this right triangle is 3. It is like that. It is r. The base of our right triangle is the height of the cone, which is 4, and the slant height, which I gave it already in the problem, but let's say you didn't know, you could calculate the slant height. First of all, this is a right triangle that is commonly memorized, 3, 4, 5. So L is 5. But let's say that you didn't know that 3, 4, 5 is a common right triangle. Those are common dimensions for a right triangle. You could calculate it. So you have a squared plus b squared equals c squared, Pythagorean theorem. So if we plug in, we can have 3 squared plus 4 squared equals, in this case, L squared. 3 squared is 9 plus 4 squared is 16. We're going to have to take the square root of both sides to get rid of the L squared. And 9 plus 16 is 25. We're going to have the square root of 25 equals L, and the square root of 25 is 5. Now, to set this up, we're going to solve this in 2 ways. One, using a formula that you can just get from Google, but 2 is, I imagine, where the formula came from, although I'm not sure about the history. It is a way that you could derive the formula using integration. So for that concept, let me redraw my cone again because we're getting a little messy. If we imagine this cone, once again, this is supposed to be the same cone. And if we take like a little, say this cone is made of clay, and we take a razor blade and we push it downward, you know, perpendicular and everything like that, so that it's nice and just perpendicular. And we move that in a downward direction through this cone. We're going to cut into it, right? And the shape that we will get, because this is a right cone, will be a circle. It will actually be a perfect circle because a right cone is built of perfect circles all the way through. So this circle has a center, and from the center out to the outer edge is r, meaning the radius. Same thing at the base, the circle, there's an r there. So if we were to take this imaginary razor blade, let's say it doesn't actually cut, let's say it just you know, pushes down through, right? So it pushes out a circle, and it just pushes out these little circles as it goes along, like slicing pepperoni, I guess. And if you started at what I have here is the pointy end of the cone, and you keep slicing this, I'm going to make straight lines instead of circles, but if you were to keep slicing this over and over and over again, and you slice it all the way from the pointy end to the base, an infinitely number of times. So you have infinitesimally small circles, an infinite number of them. If you were able to add up the areas of all of those circles, that would give you the volume of the cone. That's the basic idea that we're using. And anytime you have to add up an infinite number of something, that is a good time to use an integral. So that's what we're going to use. That's basically what an integral means to do. So we're going to say volume equals integral from a to b, which those are our starting and ending positions. And as was already said, our starting position is the tippy top of our cone, and our ending position is the base. So if we look at our picture where the cone is on the Cartesian plane, our starting position is at the origin, 0, 0. So a is going to equal 0, A equals 0. And we're going to keep making slices as we move along in this direction until we get to the base. And the base is set at the h value. I guess just say that. It's the length h along the x-axis. And the length of h is 4, because that was given in the problem. So b equals 4. A and b are meant to be the x values of those 2 points, the starting point and the ending point. Then what else are we going to need? We're going to need the integral from a to b of the area with respect to x. That would be okay to say that way. Dx. The dx is because we moved along the x-axis, and the area we're going to need in terms of x. So the area, what is the area of our slice? As I said, our slices are circles. Area of a circle, we can do that here. Area equals pi r squared. But we can't use r. We could plug in pi r squared, but the problem is we can't take the integral of r with respect to x. The reason is r is not a constant here, and to prove that, you just, as I make different circles at different slice points, the value of r is going to change. So like in this picture, you see 3 different r values. Clearly each one of them is a different number value. The first one on the left there is going to be smaller, the next one will be bigger, and the next one will be bigger. And that'll be true all the way through there. But conveniently, you notice that the r value always equals the y value of the point, this point on the line that makes the hypotenuse of the right triangle. So as I draw little points on this hypotenuse of this right triangle, any one of those points, the y value of that coordinate is the radius of a slice. So that's very convenient. So we're going to solve that by doing, so if you want to say, we can say the area with respect to x equals pi y squared, because y is equal to r in this case, as I just showed. Once again, though, the problem is we need it in terms of x, not in terms of y, because we're slicing horizontally along the x-axis, so we need an x variable. We could try to use the Pythagorean theorem, because we had x squared plus y squared equals L squared, but we're going to end up with both an x squared and an L squared as the end result. And L in this case is not a constant, because that represents a length along the hypotenuse, and that's also going to change. So we really can't use that. Another thing that we can use, however, is this hypotenuse represents a line that continues to extend out to infinity this way, continues to extend out to infinity this way, and that line has an equation which happens to be really easy to discover. The equation of a line is y equals mx plus b. M in this case is the slope. Not really in this case, always. M is the slope. The b is the y-intercept. And the y-intercept is easy because the y-intercept, as you can see from my picture, is 0, because I intentionally laid the cone on the Cartesian plane so that the point of the cone touches the point 0, 0. So the place where our line for the hypotenuse of our right triangle, the place where that line crosses the y-axis is at the y value 0. It's given. So plus 0, y equals mx plus 0, we can ignore the 0, we can ignore the b. So we just have to figure out m, which is the slope. Slope is equal to rise over run. You could pick any height here that's on this line and use the values at that point to give us our rise over run. But conveniently, we don't have to do any more calculating. We have 2 nice round, easy values given to us in the setup of the problem, and that's the 3 and the 4. there's a point up here at the corner. You see that at the corner of the right triangle, that is the point 4, 3. Okay, and we can just use this point, and as we travel to that point, we see that our rise is 3 and our run is 4. So rise over run, it's going to be 3 over 4. So y equals 3 over 4 times x. Now this 3 over 4 times x, we can plug in for y. So we get the area with respect to x equals pi times 3 over 4 x squared. Now I want to go ahead and plug that into our integral. So volume equals the integral from our starting point on the x-axis, which is 0, to our ending point on the x-axis, which is 4, of the area of our slice, which that formula is pi times 3/4 x squared dx. Now all we have to do is solve this, and we can pull the pi on the outside of the integral because it is a constant. I'll do some steps here to save some writing. So to square 3/4 x, everything in there is related to one another by multiplication or division, and so we square the term by squaring each of the pieces of the term. So 3 squared is 9, 4 squared is 16, x squared is x squared, and the 9 over 16 we will also be able to pull outside of the integral because that is a constant. 9 over 16 times integral from 0 to 4 of x squared is the only thing we have left inside, dx. So next step, volume equals, I'm going to break down this 9 over 16 into some component parts to allow simplification easier. So 9 is made, well, let's keep the pi first. We need the pi. 9 is made from 3 times 3. 16 is made from 4 times 4. I don't really see the need to break down those 4's into primes, but if you did, it would be 2 times 2 times 2 times 2. But 4 times 4 is good enough. If there's anything that can be broken down, we can easily see now. What's left from the integral will be, to take the integral of x squared, we first raise the power, so x to the third, then we divide by that number, divide by 3, and we're going from 0 to 4. And to solve, we would have to plug in the 4 for x, then subtract plugging in 0 for the x. But when we plug in 0 for the x, 0 cubed is 0, 0 divided by 3 is 0, so we're going to end up subtracting 0. So we can actually ignore the lower bound, which is 0. So that's what we're going to do. So we have v equals pi times 3 times 3 over 4 times 4 times, we're going to have 3 4's on the top because that's what 4 cubed is, over top of 3. Now we can easily cancel some things. One of the 3's on top cancels with the 3 on the bottom. 2 of the 4's on the bottom cancel with 2 of the 4's on the top. On the bottom we're left with a 1. On the top we're left with 3 times 4, which is 12. 12 divided by 1 is 12. So we have 12 pi. Volume equals 12 pi. So that is our volume. Now let's say we're kind of novices and we feel like we know how to use integration, but we're not really sure if we did it right and we want to check our answer. If you go to Google, you can actually just Google a formula for finding volume for a right cone, and the formula that I found was volume equals pi r squared times h over 3. So once again, from our given information, r is 3, so 3 squared times, and h was 4. 4 over 3. When we multiply this all out, the 3 on the bottom of the fraction will cancel with one of the 3's from this power. So we're left with 3 times 4, which is 12, and a pi. So we checked our answer, and everything was good, and that was the volume of our right cone. Now we're going to move to surface area, and I'm going to need a new paper. Here's one. So, okay, so surface area. First, let's get our cone back up here. It's supposed to be a right cone, so if you were to slice it perpendicular, you would end up with a circle. And we have R, H, L. We have R equals 3, H equals 4, L equals 5, and what we calculated was volume equals 12 pi. Now let's find the surface area. And we're going to do the same thing. We're going to lay it on the Cartesian plane. We're going to use a right triangle that's rotated around the x-axis and have the point sit the origin. And as we rotate that right triangle around the x-axis, we end up with a right cone. And once again, this is a 4 for H, a 3 for R, and a 5 for the hypotenuse or the slant height. This time we're going to do something very similar, but something a little bit different comes into play. So if we take our right cone that's laying on its side, oops, well, this one didn't work out so good as my other pictures, but use your imagination. That's a right cone. And if we do the same thing, we take our little imaginary pepperoni maker here, and we push downward perpendicular through the cone, and we take a slice out of that cone. This time we have to concern ourselves with the thickness. So if we take this little slice, we're going to have R, and in this case it has a thickness DL, and unfortunately I do not know exactly why we need to concern ourselves with the thickness when adding up infinitely many slices of circumference, whereas we did not when adding up infinitely many slices of area. I wish I did know the answer to that question, but I don't. So if we add up all of these little circumferences, then that will give us the total circumference if we also multiply by dl. So surface area equals integral from, once again, a to b, being the starting and ending points of our travel along the x-axis, of circumference times dl. dx. So the dl represents the tiny change in length of our infinitesimally small piece of circumference, or piece of surface area. Our infinitesimally little small piece of surface area, which is basically the circumference of a circle, but maybe not exactly the same as the circumference of a circle. It's whatever the thickness of this almost 2D circle is. That's our dl. And to figure out dl, you have to pull something from the formula for arc length, which, let's put that over here. So the formula for arc length, let's say you have some kind of random curve, and I'm only going to draw part of the curve on purpose. Let's say you have this curve, right? But this is just a piece of a curve that runs from A to B. If you want to figure out the length of that curve, yeah, you can use the formula. I think they designate arc length with an S, equals the integral from A to B of the square root of 1 plus the derivative dy dx, the derivative of y with respect to x, squared dx. So that would tell us the length of this line, arc because it's curved, this arc from A to B. So we're going to have to use that is dl basically. And our circumference, the formula for a circle, this formula for circumference of a circle, which is once again the shape we have is a circle, or slice is a circle shape. Circumference equals 2 pi r. So surface area equals integral. Oh, sorry, I didn't realize my video was covering that. Oh well, you'll see it again in a second because I'm going to write it for dl. The integral from A to B, circumference is 2 pi r times dl, which you can't see because my video is covering it, but dl is the square root of 1 plus the derivative of y with respect to x squared, and then the whole thing is dx because we're traveling along the x-axis as we make these slices. So yeah, we're just about there. So surface area, once again, the a and the b are still 0 and 4 for the same exact reason. We're moving along the x-axis from the x value of 0 to the x value of 4. We have 2 pi. R is going to be the same thing it was in dealing with volume. It's going to be whatever our y value is in this right triangle, and our y value is found by the formula. It's y equals 3/4 x. So 3/4 x is what we're going to plug in for r. 3/4 x times the square root of 1 plus, so now we do dy dx. So dy dx of, so the y, as we already found, y equals 3/4 x. So the derivative of y with respect to x is the derivative of 3/4 x. So the derivative with respect to x of 3/4 x equals 3/4. X just disappears when you take the derivative. 3/4. And it is still squared, and we still have our dx on the outside here. Now, for some solving, surface area equals, we're going to have a 2 on the top of our fraction and a 4 on the bottom, so that cancels a little. So, and we're going to move it to the outside. So we're going to have 3 over 2 pi. We'll leave that inside for now. The square root, sorry, not square root, the integral from 0 to 4 of x, and underneath our square root, we're going to end up with 9 over 16 after we square the fraction. So let's change this 1 to 16 over 16 plus 9 over 16 dx. 16 plus 9 is 25. So we can actually take the square root of that, and we can pull it on the outside because I'm running out of space here. Surface area equals 3 over 2 times, when we pull out our everything under our radical, we're going to end up with the square root of 25 over 16, which, taking the square root of the top and the bottom, will be 5 over 4. So we'll have 5 over 4. And we still have pi. Integral, and we'll go ahead and take the integral once again because I'm running out of space. So we're only going to be left with the integral of x dx, and the integral of x is just x squared over 2, and we're going from 0 to 4 once again, and once again we can ignore the 0 for the same reason as last time. So we're going to end up with surface area equals 3 times 5 over 2 times 4 pi. We're going to end up with 4 times 4 on the top, because that's what 4 squared is, over top of 2. So we can cancel out one of those 4's that's on the top with the 4 on the bottom. Then if we were to multiply 2 by 2 on the bottom, we would get 4, which cancels out with the other 4 on the top. So we're only going to be left with 15 pi. Surface area equals 15 pi. And that, of course, would be units squared, whereas our volume is units cubed. 15 pi. And once again, we can Google a simple formula and check to see, did we set up our integral right? Were we on the right path when we were thinking through this conceptually? I have a little bit of room. I'll try to put it in right here. Kind of in this little space right here. So a formula that you would get is for surface area. Oh, something that I'm missing actually. So the formula is going to give us a surface area of, say if you had an ice cream cone, it's going to give you just the cone part, but it's also going to give you the base. We didn't add in the base. So if we add in the base real quick, the surface area of the base is just the area of a circle, so which is pi r squared. R was 3, so we're going to end up with 3 squared, which is 9 pi. So we have to add 9 pi to the 15. So total surface area is actually equal to 24 pi, because that's what our formula from the internet is going to give us. So the formula is pi times r plus the square root of h squared plus r squared plus r squared. I think that's it. Yeah. Now we can start plugging everything in. So surface area equals pi times 3 plus the square root of, for h we're going to plug in 4. 4 squared is 16 plus r is 3. 3 squared is 9. So under the square root, we're going to end up with 16 plus 9 is 25. The square root of 25 is 5. 3 plus 5 is 8. So in the parentheses, we have 8. We still have a pi on the outside and a 3. 3 times 8 is 24. So 24 pi equals 24 pi, the total surface area. And the volume was 12 pi. 12 pi units cubed, 24 pi units squared.